This video is about the magnetic field. Let's first look at an experiment. A bar magnet is hung on a thread. This can rotate freely. Before starting the experiment, the south pole of the bar magnet points to the right and the north pole to the left, as seen from us. Let's see if we can change this direction. To do this, I turn the bar magnet so that the south pole and the north pole point in a different direction. After I let go of the bar magnet, it starts to turn back and forth. It takes so long that I'll show you this in a fast run. Only after I move the bar magnet back into position so that the south pole is pointing to the right does it stop rotating. This is the only stable alignment. But why? I remove the bar magnet and put a compass under the clothespin. The compass shows us in which direction the north and south poles of the Earth are. We remember that the south pole of a bar magnet pointed to the right, where according to the compass the south pole of the Earth is. That's strange. We had found in an experiment that two identical magnetic poles repel each other. To explain this, we need to take a look at the Earth. As you probably know, the Earth rotates on its own axis. Let's position a huge compass on the Earth. The compass needle is nothing more than a bar magnet with a north and a south pole. The north pole of the compass needle points in the direction of the north pole of the Earth, and the south pole of the compass needle points towards the south pole of the Earth. How can we explain that? The Earth has two magnetic poles like a bar magnet. Let us imagine that the Earth rotates around a huge bar magnet. The decisive factor is that the bar magnet at the geographic north pole has a magnetic south pole. At the geographic south pole it has a magnetic north pole. This explains why our freely rotatable bar magnet pointed with its north pole to the geographic north pole, and this was attracted by the magnetic south pole. However, our magnet is very far away from the magnetic poles of the Earth. How does the magnetic sense where north and where south is? This has to do with the magnetic field around the magnet. Let's take a step-by-step look at what the shape of the magnetic field of a bar magnet looks like. To do this, I first put a compass around the bar magnet. The compass needle aligns itself with the bar magnet depending on its position. The tip of the compass needle is the magnetic north pole. This points in the direction of the magnetic south pole of the bar magnet, and the flat end of this compass needle points in the direction of the north pole of the bar magnet. If you take a lot of small compass needles instead of a single compass needle, the following picture emerges. You can see lines that point from the north to the south pole. If you change the alignment of the bar magnet, the alignment of the compass needles also changes, so that we can again see lines that point from the north to the south pole. The shape of the magnetic field can be illustrated even better by placing a white cardboard over a bar magnet and sprinkling small iron fillings on the cardboard. You can see 2 points at which many iron fillings are arranged. Below these 2 points are the end of the bar magnet. The magnetic force is strongest there. Starting from the 2 poles of the magnet, the iron fillings are arranged in straight and curved lines. Let's look again in the animation at the examination of a bar magnet with several compasses. If you now connect the alignment of the individual compasses with lines, you get the following picture. Here you can now see the shape of the magnetic field around a bar magnet. The individual lines are called magnetic field lines. These magnetic field lines never intersect. The direction of each magnetic field line is shown with a small arrow. Internationally, scientists have agreed that the magnetic field lines point from the North Pole to the South Pole. The direction of the magnetic field lines is not very important at this point, but it is helpful to know in later lessons if, for example, you want to determine the direction of the Lorentz force. The density of the magnetic field lines, that means the number of magnetic field lines in a certain area, indicates how strong the magnetic force is at this point. At the two ends of the bar magnet, the magnetic field lines are very close together, since all magnetic field lines exit from the North Pole and enter the South Pole. Accordingly, the magnetic force is greatest there. To the side of the magnet, the magnetic field lines are not so close together. The magnetic force is also significantly lower here. Next to the bar magnet is a so-called horseshoe magnet of particular importance. If you examine the shape of the magnetic field of a horseshoe magnet with a compass, you will find that the orientation of the compass in the center of the horseshoe magnet is the same everywhere. You can see this even more clearly if you use our many small compass needles again. Only in the outer area of the horseshoe magnet do the compasses show in different directions. The magnetic field of a horseshoe magnet can again be illustrated very nicely with the help of iron fillings. In the animation, let's look at the orientations of the compasses and the magnetic field of a horseshoe magnet. In the middle, the orientation of all compasses is the same. In this area, one speaks of a homogeneous magnetic field. In this homogeneous magnetic field, the magnetic force is the same everywhere, both in its strength and in its direction. There's an inhomogeneous magnetic field around the horseshoe magnet.